Welcome to SK Vidyayan Physics classes. I am Sri SK Das, retired Associate Professor of Physics. Let us discuss some questions on energy band and semiconductors. First question is, semiconductors are transparent to red color of light, green color of light, infrared radiation, violet color of light. Correct answer is infrared radiation. So what is the principle? Now consider a material, say silicon or germanium. The energy band shown in the figure. Upper is the conduction band and this is the valence band. So minimum energy required for electron to be transferred from valence band to conduction band is called energy gap. That is the lowest level of conduction band and uppermost level of the valence band. That difference in energy is called energy band. Now suppose a radiation has energy h mu which is less than energy gap. What happens? The amount of energy that is incident on the semiconductor is not absorbed because electrons will not receive energy from the radiation as the energy gap is more than that of h mu, energy of radiation. In that case, the energy is transmitted and we say that the semiconductors are transparent to the radiation. Now, infrared radiation has wavelength in the range 780 nanometer to 1 millimeter. If we use the expression that h mu, energy of radiation, mu is c by lambda, substituting the values of h and c, we express energy gap as 1242 electron volt nanometer per lambda in nanometer. Now, if you substitute the value of lambda from 780 nanometer to 1 millimeter, then the energy of radiation varies from 1.59 electron volt to 0.0012 electron volt. This is definitely the energy is less in comparison to energy gap of either silicon or germanium. So in that case, the radiation gets transmitted without being absorbed. So the semiconductor is transparent to infrared radiation. Question number 2. An intrinsic semiconductor, when heated to very high temperature, it behaves like N-type semiconductor, P-type semiconductor, metal and intrinsic semiconductor. Answer is intrinsic semiconductor. Usually we think that when semiconductor is heated, because of the formation of large number of hole electron pairs, number of holes in valence band increases and number of electrons in conduction band increases. But we say the conductivity increases, but we cannot say that the semiconductor has same conductivity as that of metal if you increase the temperature. It is not possible. If you raise the temperature of a semiconductor, the intrinsic carrier concentration increases, but the concentration of electrons cannot be equal to that of the concentration of electrons in case of metal. So one reason is that you consider intrinsic semiconductor at high temperature as metal. Second reason, for a metal the energy gap is zero. An experimental study shows that the energy gap of a semiconductor, say silicon, Eg as a function of temperature is 1.21 minus 3.60 10 to the power minus 4 T for silicon. This shows that at absolute zero temperature, energy gap for silicon is 1.21 electron volt. And if we increase the temperature, a temperature reaches where the semiconductor has energy gap equal to 0. But this is not possible because at temperature 3361 Kelvin only the energy gap vanishes. But melting point of silicon is 1414 degrees Celsius. So with consideration of these two regions, we cannot consider intrinsic semiconductor to be metal if temperature is high. So intrinsic semiconductor remains intrinsic at high temperature. Question number 3. At 0 Kelvin, that is absolute 0, an intrinsic semiconductor behaves like superconductor, perfect insulator, N-type semiconductor, P-type semiconductor. Answer is perfect insulator because at absolute 0 temperature, the electrons in valence band have 0 thermal energy. So they cannot be excited from valence band to conduction band. As a result, at absolute 0 temperature, there are no intrinsic carriers in semiconductor. Hence, no transfer of no conduction of current in intrinsic semiconductor at absolute 0 temperature. That is why it behaves like a perfect insulator. Next question is, a sample has band gap of Eg. The maximum wavelength emitted due to combination of electron in a conduction band and hole in a valence band is lambda maximum Sc by Eg, Sc square by Eg, Ch square by Eg, H by Ceg. Now, an electron in a valence band requires energy equal to forbidden gap to be transferred to conduction band. Similarly, when an electron in a conduction band jumps to the hole in valence band, that is recombination occurs, then energy is transmitted. So maximum wavelength means minimum energy. Minimum energy, say the lowest level of conduction band and upper level of valence band. The difference between these two in energy terms is equal to energy gap. If H mu equal to energy gap, that is Eg, then lambda maximum equal to Sc by Eg. That is, the radiation has minimum energy that is equal to energy gap. So correct answer is lambda maximum Sc by Eg. Next question is, if NH and Ne be the number of holes and conduction electrons in an intrinsic semiconductor, then what is the correct choice? Number A, NH greater than Ne, NH equal to Ne, NH less than Ne, NH not equal to Ne. In intrinsic semiconductor, as you know, at any temperature, the number of holes is same as number of electrons. So correct choice is, answer is B. Number 6. In a semiconductor, the current flow depends on mechanism of first choice drift, second choice diffusion, third choice both drift and diffusion, fourth choice neither drift nor diffusion. Answer is both drift and diffusion. In a conductor, you know that if you apply electric field, electrons drift and constitute the motion of the electrons in the conductor constitute electric current. Similarly, in case of semiconductor, the electrons drift, holes drift, that is the charge carriers drift, constituting the current. But besides the phenomenon of drift motion of charge carriers, we can also have diffusion of charge carriers in semiconductor that happens because of a non-uniform concentration of carriers, which never happens in metal. In metal, the current flow is because of drift motion of electrons, but no diffusion occurs in metal. Next question. Temperature coefficient of carbon resistor is 0, positive, negative, both positive and negative. Since carbon is an semiconductor, the resistance decreases with rise in temperature, hence temperature coefficient of carbon is negative. Next question is, pure silicon at 300 Kelvin has equal electron and hole concentration of about 1.5 10 to the power 16 per cubic meter. Doping by indium increases the hole concentration to 4.5 10 to the power 22 per cubic meter. The new electron concentration in doped silicon is, there are three choices given. So what is the principle? Principle is that suppose at any temperature for silicon or germanium, that is intrinsic semiconductor, the number of electrons in conduction band is same as number of holes in valence band, and that is the intrinsic carrier density Ni. And if that semiconductor, say germanium or silicon, it is doped with pentavalent impurities or trivalent impurities, then if number of electrons density is Ne, number of hole density for that particular material is NH, then the product NeNH is equal to Ni square. So here in our question Ni is given and hole concentration, that is NH, is given. We can find out Ne by substituting the values, which comes to be 5 into 10 to the power 9 per cubic meter. This shows that the electron is minority carrier because it is doped with indium, so it is a p-type semiconductor. In p-type semiconductor, the majority carriers are holes and the minority are electrons. Next question. A semiconductor has electron density N and hole density P. The mobility of hole is mu P and that of electron is mu N. If E is the charge of both electron and hole, the conductivity of semiconductor is sigma Ne mu N, sigma Pe mu P, sigma E whole into N mu N plus mu P mu P. Fourth is E mu N plus mu P. What is the correct answer? Correct answer is C, that is sigma E times N mu N plus P mu P. So how can you find out? Say you consider a sample, a specimen of crystal, and cross section area be A, and let us consider electron density inside the material is Ne, and choose the length of the material to be V. V is the drift velocity of the electrons. Now the current, if you connect the material, the specimen, to a source of EMF, then the current flows, and the current I equal to area drift velocity VE N into E, because area into velocity is the volume per unit time. If you multiply the number of electrons per unit volume, then this becomes the total number of charge carriers contained in the sample of length VE. And if you supply a source of EMF, then this amount of charge carriers passes through the other end in 1 second. That is why the current is AVE Ne into charge of electrons G. So current density is, dividing current by area, is VE Ne into E, or J equal to sigma E. Sigma is the conductivity, E is the electrical intensity, equal to VE Ne, or sigma equal to N E small e VE by E. What is the fact? The expression VE by E, that is the drift velocity per unit electric field, which is called mobility of the electron. So conductivity equal to number of charge carriers per unit volume, that is carrier concentration. Say electron here, we have taken charge of the particle E and mu. So N E mu is the conductivity because of the motion of the electron. Similarly, we can show that conductivity due to the whole part of motion is sigma equal to E P, that is the whole concentration, and to mobility. So taking, because in the semiconductor the current flow is due to the charge carriers, both charge carriers, that is electron and holes. So sigma equal to E times N mu N plus P mu P. So the choice is C. Next question, that is, an electric field is applied to a conductor if the number of charge carriers be n and the average drift velocity is v. When temperature is increased, both n and v will increase. N will increase, v will decrease. V will increase, but n will decrease. Both n and v will increase. Answer is B. Now, what is the explanation? We have seen that conductivity equal to charge, that is, which is same as that of the electron and hole, times concentration n, mobility mu n plus p mu p. So, as temperature rises, the drift speed decreases due to collisions, which is same phenomenon in case of conductor. In a conductor, if you increase the temperature, drift speed decreases because collisions become more frequent. So also in semiconductor. So if drift speed decreases because of the rise of temperature, then the mobility of the charge carriers, whether it is hole or electron, they decrease. Now, so mobility decreases means it shows that from the expression conductivity should decrease. But we know the conductivity of intrinsic semiconductor increases with rise in temperature. But here, because of the mobility of electrons and holes decreases, the conductivity should decrease. But in contrast, when you increase the temperature, the carrier concentration, that is the formation of electrons and holes, become very rampant. The number of carriers, holes and electrons, the density increases very sharply. As a result, this phenomenon, rise of concentration of carriers, becomes dominant, as a result of which the conductivity of intrinsic semiconductor or semiconductor increases with rise in temperature. Let us hope that these questions will be of immense help for the students. Thank you.